As in the intro, I'm here to talk about recreating Wolfenstein in F# and .NET. It's about me, I guess. I've been working in tech for a long time. I work at a company called Blackdot Solutions at the moment as the CTO. We do OSInt investigation software. Um, yeah, you can find me there. The code's all on GitHub, so keep note of that link. I'm currently working on a whole bunch of kind of game and crazy related stuff just for fun. You can find some of that on my GitHub, some of it in other places. But I don't want to dwell on that because we've got a lot to get through. 45 minutes, it's not long to talk about the range of topics I'm going to cover, and we might not get to the end of the session. So I've kind of structured this in order of what I perceive as interestingness. So I can kind of keep my eye on the time and present the interesting bits. The source code can be found at the link you can see on the screen. I wrote it, I think, a year and a half ago, and revisited it when I started talking about it this year. It's reasonably legible. Considering I didn't know what I was doing when I set off, that's quite surprising. So you can kind of pick your way through it, particularly if you've heard this talk, I hope, which will give some of the concepts behind it. And if you're more on the C# side, there's a Blazor and C# version of a renderer also in my GitHub. I didn't quite get around to implementing the AI, but it does render. And it's, again, I think it's probably a little better written than the F# one because I knew what Wolfenstein was doing at that point. So Wolfenstein 3D, why recreate it? It was a really formative moment for me when Wolfenstein came out, and I think it was in '92. And I literally remember running around the house. I lived with my parents. I was probably been about 16, I guess, and I was running around the house, extremely excited, and screaming, "This changes everything!" Because I'd never played anything so colourful and fluid that was in 3D. And at that point, I'd already written lots of code. I was, typical sort of 8-bit bedroom code in the UK, cranking out 6502 assembler and all this kind of stuff. So I had to go writing a Raycasting. I was like, I wonder if I could figure out how this worked. I could kind of see how it worked. So I wrote one in C on a probably a 80386, and I guess in Turbo C, which is what I was using at the time. But it was interminably slow. Like, it ran at no frames per second. And there was weird gaps in the textures, and there was a fisheye effect, which I now understand what was going on, but at the time I had no idea. It was interesting, and I was sort of, amazed at what the id software guys had accomplished. In 2022, I guess that's last year. I kind of woke up one day. I thought I have to try this again, and I really don't know why. But it was like I'd got this. I got it between. I really got this idea. I have to do this. I have to get this. Understand this, and I started building it out again. So quick demo. I have to do a bit of screen hopping in this, so hopefully I've got things set up okay so we can see it. This is it running in a browser. So I've done a browser version and a desktop version, and we'll talk a bit about that. And you can see that if you remember Wolfenstein, you probably can't hear the audio, but there's audio in here. The sort of the German guys running around, and if you played Wolfenstein back in the day, this will be extremely familiar too. So it's the gameplay is mostly there. It was great fun, and I had a whale of a time writing it. So I'm just going to refresh that to set it back to the start so we don't get the sounds while I'm trying to talk about it. So that's it running in the browser. If we get time, we'll pop it up on the desktop later, but it looks exactly the same. So before we get into sort of how it works, there's some kind of important principles behind Wolfenstein 3D, which I knew going in, but they're really easy to forget because it's quite convincingly 3D when you're playing it. I know by modern standards, it's not this amazing graphical wonderland in a modern game, but it's still it looks and feels 3D to you as a player. It's really a 2D game. There's nothing three-dimensional about it. You can't go. There's no tunnels underneath things. It's strictly on a 2D grid. And in fact, the id Software guys, as I understand it, used their 2D level editor from things like Commander Keen in the previous games, if you remember that sort of time period, to do the level design for Wolfenstein 3D, which was a tile map editor. So it's strictly 2D and everything is on a grid, including the way the enemies move, which I didn't quite realize when I started, which was quite made for an interesting moment or two. And if you want to look at the source is online and it's pretty readable. It's pretty. I started life as a C developer in my professional life, and it's pretty readable as a C code base. It's got some cunning tricks in it in places, which can make those bits a little bit obscure, but it's pretty readable. So there's some sort of important principles. This is just a view of the grid. So this is the first level of Wolfenstein in a sort of level editor. When I was developing this, I used Maphead42, which runs in DOSBox on my Mac. It's an old, goodness knows when it was written, but it lets you inspect the levels, edit the levels if you want to edit the levels. I was really just inspecting the levels, but you can see it's strictly grid based, and if you see my cursor on the screen, the cyan G, that's a guard, and there's plants, and the player is there, or there rather. I forget which one. There, that's the player. It's strictly grid based. The whole game works like that, and that's what allows it to work so quickly, as we'll see as we get into it, and how it works so well on low spec kit by modern standards. It was quite high spec at the time. I didn't plan it as such. I didn't sort of, which is probably a bit silly, really, but I didn't sit there and think this is how I'm going to build this thing. But I just sort of thought, I'll get this thing going without textures. I'll get a plain view of a Raycaster working without textures. I'll add some textures and see if I can figure out what went wrong last time I did it. When I'll get the Wolfenstein graphics and maps loading, and hopefully they then just drop into my Raycaster, and then I'll add the enemies and the AI and things like that. Which was fine, and that worked quite well. It was quite exploratory, but I didn't know anything about Raycasters. I didn't really know how Wolfenstein worked as a game, other than as a player. So sort of exploratory approach seemed reasonably sensible to me. About halfway through, I thought, it'd be fun if this runs in .NET on the desktop, as well as in the browser. So in the browser, it's using Fable, which is an F# to JavaScript transpiler. So in the browser, it's running using Fable to create JavaScript from the F#, and it's rendering to the canvas. In the .NET desktop version, it's running in .NET. I think it's .NET 6. It might be 7, perhaps. It doesn't really matter. It's a fairly recent .NET, cross-platform .NET. And it uses Silk as an interface to the graphics hardware, and we'll come to that a little bit later, hopefully. I don't think I referenced any source code until I got to the AI, but I was definitely looking at other Raycasters. So there's a few JavaScript ones out there. There's I don't think I came across a .NET one, but I could be wrong. But there's a whole bunch of people writing simple Raycasters that you can go and have a look at, and that helped me figure out some of the concepts behind how they worked. So Raycasting, I've used that word a lot. So what is it? Essentially, if you think about the view of Wolfenstein we're looking at, we've got a rectangle on the screen, and for every column of our viewport, we're going to draw a line from the player, from us, to that viewport, and see if we intersect anything. So we'll cast a ray. And if for example, if our screen size is 320 by 256, and people who are my age or older will remember why I'm using that resolution. But if our viewport is 320 by 256, I'll catch you. Is it 256? Doesn't matter. I'll have 320 rays to cast across, one for each column of our display. So we cast those rays across, and we're looking for collisions with a wall. And we'll forget about enemies for a minute and just think about wall collisions to get the wall collisions working. So how do we cast a ray? How do we actually shoot a ray across our viewport? Like, the obvious way to do it, the sort of naive way to do it, is to break the line down into lots of small sections and walk along it, and testing at each point if we've hit one of our walls being these squares, these cubes, because it's on a grid. But they're not lines, they're actual cubes. The problem with this approach, though, is that you can miss a wall. You could step over a wall. And one fix to that would be to make increasingly tiny steps. And you could probably make them so small that if you ever missed a wall, it wouldn't really matter. It'd be right on, but be right on an edge case. You'd probably get a bit of flickering, but the cost would be really high. You're gonna have to start making lots and lots of these tiny steps each time for each line across your screen, each column across your screen. So that's not a good way to go. So what you can do instead is think of your map like another sort of 2D canvas and draw a line across it using a line drawing algorithm. And this will really start to make ray tracing make sense to me. Until I got this in my head, that I was drawing a line, thinking of a map as a set of pixels almost. I find it quite difficult to get this in my head. But once I realized I was drawing a line, it started to make sense to me. And if you draw a line onto a 2D, if you've ever done any kind of primitive graphics work and you're drawing a line, you've got your array, your pixels, which you think of this as a set of pixels. You start here, and if you're drawing a line in this angle, you don't draw this smooth line. You're drawing this pixelated step-based line. And that's, if we draw arrays like that, we can't miss anything. Eventually we will hit we'll hit a grid element with something in it, and we can decide what to do. Once we've hit the grid element, we can backtrack from the element we've hit and figure out where we hit it. And that makes this many times cheaper than the series of steps to do, and it's also accurate, which is quite important unless you want a crazy display. You could use, in theory, I guess, any line drawing algorithm for this, of which there are many. And if you do sort of a Google for line drawing algorithms, you'll find many, and there's many interesting ones. Some deal with aliasing, some don't. It's one of those rabbit holes you can go down. It turns out the line drawing algorithm I was familiar with before I came into this was Bresnan, which I'd used previously. But when I looked at the raycasters, that are out there and the sort of literature on them, most people are using something called digital differential analysis, or DDA, which sounds horrifically complicated, but isn't that complicated, again, once you get your head around it. But in any case, it was this kind of low resolution line analogy that made sense of it for me. I was like, oh, I get this now. Okay, I see how this works. I suspect when I did this back in '92, I probably did a series of little steps. That would have been pre-internet and pre-being able to kind of research this stuff easily. Obviously, this is quite easy to do these days. Actually, I find DDA easy to explore from pseudocode, but essentially what you do is let's just look at the pseudocode. I find it much simpler to explain through pseudocode. You figure out your initial distance to the next X point and your initial distance to the next Y point from where you are now. And then you start tracking the total distance that you've traveled X and Y. And essentially what you do is you walk along one axis until you've traveled further than you have in the other axis. And then you swap it around and start walking in the other axis. And each time you swap it round, you've moved along an entire element in the grid on that axis. And you can see that in the pseudocode here, I hope. There's our sort of initial distance to the X and Y. Actually, if we just go back a slide, this diagram would be helpful. The initial distance to here. We load that up there into a total distance. And then we do this. Let's move to the next X. Let's move to the delta distance X is the distance to the next X point, to the next X point. And at some point, we'll have traveled further in the X distance than we have in the Y distance, and we flip it around. And then that will start stepping up. So you'll go with step, step, step across, step, step, step up, step, step, step across. In general, you're going step, step across, step up. Depends on the steepness of the line. And that's essentially how you cast the line, cast a ray. And you just keep doing that until you hit a wall. Once we've hit a wall, we need to figure out how high the wall is to display. So you think about the sort of Wolfenstein view, we need the sense of perspective. Further away things are, the smaller they are. So we need to calculate that height. This is the thing that tripped me up the first time I did this back in '92. I was measuring this distance here to the wall, which is kind of intuitive. Here's the player, here's the distance to the wall. We use that to calculate the height. But that results, as you move out, that results in a strange fisheye effect. So what you actually do is calculate the perpendicular distance from the camera plane to that point. So the right angled distance from the camera lens to that point, and that gives you the flat, gives it nice and flat for you. Which was quite interesting to me. I'd figured out why I got this wrong in 92, at least. I don't have the code anymore. It was on a floppy somewhere, but why I thought I got this wrong in 1992. So with all that out of the way, we can look at some code, and hopefully I've got this racked up good to go in Rider, which I'm on a Mac, so I've been using Rider for some time. The bulk of it is in this render scene method, and you can see here a sort of F# implementation of that pseudocode. So I talked about walking across across our viewport. So we're using a HTML canvas. It's got, it's as wide as it is as I've defined it in HTML. So we walk across that canvas from column 0 to column 1, and for each, let's get to the bit that I want to talk about. For each, we basically set the variables, so there's a delta distance x, the thing I was talking about earlier. We set up our step x and step y. You need to track, and I'll come back to that later, but you need to track which direction you're moving in, basically. So you can add if you're going to the left, you want to add -1 on. If you're going to the right, add 1 on x, for example, and top and bottom is the same with y. So we just need a sense of that to move the map on the right direction. And finally, we get to our DDA algorithm. So this is the thing where we basically just go on forever until we hit a condition. So we use a scan. There's a lot of scanning and folding in this to kind of take those loops and put them into a functional fashion. I did try to keep this in a somewhat functional style. I think there's a couple of bits that aren't quite so functional, but most of it came across quite nicely as a functional style, but it did require a little bit of sort of mind bending in places, because most of if you see pseudocode written down or you think about it, it tends to be in a more sort of procedural kind of way. But I tried to do this as an F# project, as a functional project. So, but this is the implementation of a pseudocode. We're basically just feeding into the scan our initial distances, and then we start walking through, flipping around, flipping around as we go, x and y, until we hit. And when we hit something, we then and the hit is here. If we hit something, the cell's not empty on the map. We exit the loop. We've had a collision. In this sort of setup I have here, you can never not get a collision. So there's no sort of sense of, have I escaped the map? You can't escape the map. You always have a collision. It doesn't deal with unbounded maps. Once we've got that, we need to calculate the perpendicular wall distance, and then we draw a line. So what does this look like? I just need to go into my browser. Give me 1 second, which I have the right thing running. Should be on. So if you've not used Fable before, this is the sort of, that's the transpilation step, and it'll watch your code, and like most of these things, like using TypeScript, for example, it'll track your changes and recompile the code as you go. But here's our simple Raycaster, and you can see I can walk around it. It's quite smooth, but it's pretty uncolored. It's pretty basic, really, but it's a functional Raycaster. So that's that up and running, which is great as far as it goes. I just want to add one other thing as well. You can see, let me just find the right line here. At this point, I'm just using, I'm just drawing vertical lines with a given color based on the map cell. Pardon me. And I'm also tracking what side of the cube I'm on. And if I'm on the far side, I color it one lighter, there's a light and dark going on. But the thing I just want to note is that at this point, I'm not actually, I'm not actually using like a byte or anything. I'm using the canvas functions to write out the to draw the lines. And that's not what I wanted to do ultimately. Ultimately, I wanted to do basically use a byte array, do it as it would have been done back in '92, which was write the bytes that represent the screen out directly. So when I came to add textures, which is the next step, I made a change to make it not use things like draw line in HTML canvas, but instead get the underlying pixel data, which is essentially a byte array that I mostly look at as a UINT 32 array, RGBA, red, green, blue, alpha. And each of those is 0 to 255. Each of those color components is a byte. It can be quite convenient just to think of it as a set of bytes. From a texture point of view, we've got a text with some color on it. We want to put the same color on the screen. We don't need to copy all 4 bytes at a time in code. We can just take the 4-byte representation and move it over. So that's the sort of move to the byte array, and we can take a quick look at that. Then the other thing we need to do to add textures is figure out where we've hit in the grid. So it doesn't really matter for the color. If we've hit a wall and the wall is of uniform color, it doesn't really matter where we hit on that wall. We're always going to draw the same color. But if you're going to draw a texture, we need to know where, what slice of the texture, and the texture being a little graphic, a little sprite graphic, and we need to know which slice of the texture to put in that column. So there's a little bit more maths involved to figure that out. And once we figure that out, we simply scale the source image to the right height. So like an image resize essentially. So my next step was essentially doing these textures. The flow got a bit more complicated here. Previously, I just had a canvas and I was sort of blatting stuff to it, but now I've got various images in play, and I'm doing more complicated things with the canvas. So the flow became a bit like this. We get image data. So there's 2 textures, a blue wall and a grey wall, very familiar walls to Wolfenstein players. We get the image data from them and load it into a texture object. And the texture object is pretty simple. Again, it's just a byte array essentially, or UINT32 array with some metadata. And every time we render, then when we begin a render, we get the image data from the canvas. So in the canvas, you can get the underlying image data out of it. And when I do this in .NET, I do exactly the same. I just create a byte array, a UINT32 array, and use that as a texture. But we'll come to that later if we have time. I then essentially render these colors into that byte array, and when I've rendered filled the byte array, done every single column, I output that back to the canvas, and I set the underlying pixel data in the canvas. Hopefully that makes sense. Obviously, it's using the browser and it's using F#, but I was trying to do this in a way that was similar to the kind of approach you would take back in '92. Again, the source of this you can find in GitHub. I sort of broke out. I didn't keep track of these as I went, but when I realized it was of interest to people, I kind of broke out the steps. So there is a quick example of that. Bear with me to open a different solution. Originally, I had all these open at once, and it was just too confusing. So I moved to having it in this model. It's again the bulk of the interesting codes in this render method. It's the bit that's been added here. The bit up to here is all the same as what we were just looking at, but then we start to figure out where. This is if it's a color, we just draw a line still, but that's not actually in use in this. If the map cell is a texture, if it has a texture, essentially we again here find where our texture position is, and like this here, let texture X, we go find the texture position. We get the texture that is represented by the wall, and then we basically go and use the column in the texture to output that texture, copy the bytes across to the canvas, and you can see this no longer uses a vertical line. It's using the set pixel method, which if I go to, it is setting you know, a UInt32 array, a JavaScript UInt32 array, setting an entry in that array. So it's largely the same. There's some work to load the textures. You can see here. It's not that interesting really, that code. But again, if I just go to stop this one and run this one. Run that, and hopefully, yeah, we've got a so it starts like a bit more like Wolfenstein. So exactly the same principles before. The only thing we've changed is that yeah, is that we're now rendering these textures and finding the columns, etc. And again, the textures in Wolfenstein, the walls in Wolfenstein, if you look, they have these light and dark. It's just based on the side of the cube that you've hit. And you'll see me tracking side in that code, and that's what that's about, which side of the cube are we on, and we show a light or dark texture. I wouldn't be certain I've actually got it the same way around as Wolfenstein. I think I have, but I think I have. But it's possible I haven't. I'll skip over this. If you load up the I will skip over this. Well, it's running. This is the C# version I built in a little, again, when I knew people were interested in this and wanted to talk about it. The C# version has a little mode you can switch it into that shows the rendering process, shows it casting arrays and hitting things. So that can be quite sort of fun to explore. And this is just a YouTube video I captured from that process. It's not in the F# version, but it is in the C# version, and it's quite interesting to watch, and you can start to understand how it's actually rendering things. And you can speed it up and slow it down, so you can see the detail or just let it go. So essentially, that's the Raycaster that's running in Wolfenstein. So that small one is, if you were to look in the Wolfenstein code base, which we will shortly, it's basically the same Raycaster. It's kind of been abstracted out a little bit. So it turns out that casting arrays are generally useful. It's used, for example, for enemy bullets, and it's used for collision detection. So it's been rendered away a little bit. Sorry, abstracted away a little bit. And if you want to look at the actual Raycaster, it's in that file there. But it's really the thing we were just looking at minus any rendering. So it just produces the outputs, and then you can do things with them. And again, you can find, we won't look at the Raycaster again because there's other bits and pieces to look at to get kind of complete Wolfenstein, but the Raycaster, the renderer for the Raycaster using that abstracted Ray code can be found in render.fs, which is actually where most of the rendering code is for just about everything. So at that point, I had my Wolfenstein sort of maps running, and I was feeling quite pleased by that. I felt a little bit smug. I wouldn't have felt so smug if I realized how hard the next bits were going to be. But at the time, I felt quite smug. I also at that point wasn't like loading the Wolfenstein graphics properly. I was just I just essentially captured two of them and converted them to PNGs, I think, and was kind of just doing it in a pretty primitive way. So the next thing I needed to do was get objects and enemies appearing. So not necessarily even animating them, but just having those things appear on the screen would make the world a lot more interesting. Wolfenstein, again, it's a 2D game, so all the objects that you see in Wolfenstein are 2D sprites, and you can see it if you move around things. They don't, some things don't rotate at all; they just kind of stay facing you all the time, and other things rotate in steps. They don't rotate smoothly like you would see in a modern 3D game where everything is actually in 3D. So they're simple 2D sprites. To draw them kind of in the right order so that they kind of they block each other out. If there's an enemy guard in front of a health pack, we draw them in the right or in depth sorted order. So we maintain them in a depth sorted order relative to the player. We want the things further behind to be behind things that are nearer to the player. So we maintain the sprites in a depth sorted order. And then again, this was a little bit complicated for me to get my head around at the time. But the other thing we also do, we don't want, sorry, I'm mumbling a little bit. We don't want enemies to show through walls. We want to clip them, and we need to clip them really cleanly, so that if you have a wall, you're on a corner, you can perhaps only see part of the enemy. So we need to clip them. And the way we do that is we essentially extend the raycaster a little bit to capture the depth from the player on each column on the screen. So we make as we draw our screen, we essentially draw all the walls first. And as we draw the walls, we say this wall is 200 units from the player. This one is 201 units from the player, 202 units from the player, and we use that depth then to clip the enemy. Which we'll see in a moment. Before we look at that, I mentioned some sprites moved in steps. Sorry, some sprites kind of animate in steps rather than just facing you. I call them orientable sprites. It might be something I picked up from somebody else talking about Wolfenstein, but I've called them orientable sprites. And each of a sort of orientable sprites, which is basically the enemies, have this kind of format you can see on the screen here, where each part of their animation is done in a different direction, 8 directions, so they can face in one of 8 directions, and there's 5 animation frames or whatever it is for each direction they can face. So then you need to think about which direction these sprites are facing relative to the player. And this is where my head started to explode. This is where my smugness evaporated because this really hurt my brain. I kind of was struggling to visualize it. But fortunately, we can talk about this a little bit more in a second. Yeah, you need, if you're facing a player and the player's facing you, that's easy. But if they're facing west and you're facing northeast, which of these sprites do you select? And you need to select one. So I'll talk about that briefly now. It was quite complicated to figure out, but I think I ended up doing it. I've not looked in the code, but I think I did it in the same way id Software did it, just because it magically worked with the sprites in the same order that they'd stored them. So I was like, I probably landed on something very similar to how they did it. But the way this gets figured out is you establish kind of 8 cones, 8 triangles around the enemy, and you basically all have a unit of 1 length. So these triangles just literally go around the enemy. Each of those triangles represents one of the orientations in our kind of set of orientable sprites. We then look and say, well, what's the direction of the player from the enemy? And then we shorten that direction vector so that they fit inside the triangles. If the triangles have unit 1 length, we just need to take the same direction from player to enemy and shorten it so it will fit inside those triangles, but in the same direction. And we then say, okay, that vector is a point. We use the XY as a point, and we can use that to figure out which triangle we've landed in. And if you do that, and you sequence the triangles as I happen to sequence them, you end up landing in the 0 to 7 array that id Software defined. The way they ordered their sprites, you land just right, which was kind of handy. It's quite complicated. Yeah, I find it difficult to figure out as well, as I think you can tell. Yeah, the one final thing to talk about with before we look at some code around all this is as we draw the objects, as we're rendering them, we keep track of any objects that intersect the middle of the screen, and we use that when the player fires. We use that to figure out which enemy they've hit, rather than cast array again. We already have figured out what, if anything, is in the middle of the screen. So we also track that, and then we can see this in code. So if I just open up the Wolfenstein solution, make sure I open the right one. They're the same. New window. This window. The renderer up. Make sure I'm looking at the renderer. Second. I think I'm looking at the renderer anyway. Yeah. Okay. We just need to find the right method. I'm looking at walls. So if you want to see the wall section at the top of this renderer is for the original Raycaster, the thing that draws the walls. And then we have this object section. And in here, there's some complexity around, again, around states of enemies. Enemies can have various states, which I'll talk about in a second. And we can also, is alive is slightly different, I found. So we have to pick out, if they're an orientable sprite, we need to pick the orientable sprite index. If they're not orientable, it's just a sprite. There's nothing complicated to figure out. So the thing I was talking about in terms of picking an orientable sprite, the sort of interesting code in here, is this bit here, where I break the space around that player into 8 triangles. We figure out the vectors for those triangles, which is what this is doing here. Again, it's reasonably functional. We then this is me figuring out the test point for the player, as I described. So what's the relative position of the player? And finally, we kind of iterate through those quadrants, looking for a point that is in the triangle, which is this is-point in triangle method, which is quite interesting in itself. I think I've gone to the wrong place, unfortunately. It's a bit silly. Go back. Just trying to find the right bit of code. Sorry. Yes, I was in the right place. Sorry, it just wasn't quite what I expected it. There's again, this is a wonderful thing about I find about doing this kind of project, as opposed to sort of your sort of your typical web app, is you come across fascinating things that you wouldn't normally come across otherwise. And I may say this wrong because I'm not a mathematician, but there is a system of coordinates called barycentric coordinates, which you can use to describe triangles and decide if a point is inside a triangle with relative ease. And that's what this code is doing here. There's a great Wikipedia article on it, and there's a really handy Stack Overflow article on it, which describes it quite clearly. So yeah, I find that interesting, because it's the sort of thing you wouldn't come across writing a line of business application, but you come across lots of that kind of stuff doing this kind of thing, which is really, really fun. I find, at least. Weapons in the status bar, they're pretty simple. They're just 2D renders. And again, the code for that can find in render.fs, but it's just 2D renders. But there's no sort of fonts as we would think of fonts today. It's not like a TTF font or an open font or something. They're 2D sprites again. So there's nothing, to draw the numbers, the score. You just pick the right sprites for the number and draw them. There's I'll skip through the scene because it's not that interesting, but all that stuff is coordinated through what I call the scene. And you often come across that term in games, and it just brings together all those things, sets up the sort of graphics context, calls the various renderers in sequence, and is just a sequence of renderers. And then when we've done all that, we pop all that on the canvas through drawing those points back over. Enemy AI. I'm going to move quite quick because we're nearly done, but I think we've got through most of it. Enemy AI, it's this is where I had to start looking at the code, the id software code. It wasn't obvious to me what enemies were doing, what their states were. There's a classic book, and it's called I-386. It's a black book. It's about Wolfenstein and how it works, and there's some good info on there on how the enemies behave. But the enemies are essentially controlled by turning points. So on the map, you can have, I think it says P in that editor, and when an enemy walks into them, they turn direction into whatever direction that's pointing. I mentioned things being grid-based and enemies tripping me up. I hadn't quite realized that when I got started, but it makes sense in retrospect. One of the things enemies can do is react to you. So they see you and they start coming towards you. And in my first iteration of this, they would literally see me and then immediately start coming towards me. But that could take them off grid and start missing turning points, essentially. So, and missing other important things. Wolfenstein relies on them always being aligned to those, being able to land on the center of those grid points. And if they don't do that, you get very strange behaviors happening. They'll start to slowly wander off paths and things. So again, it's about example of how strictly grid-based it is really quite interesting. Most enemies will hear sounds and come running towards you, but there's the occasional enemy that doesn't hear sounds. Interesting, Wolfenstein had quite a complicated, for the time, sound model. It would track open doors, had sound zones, and that's one of the things that makes the game quite interesting, I think, is that it allows for surprise. It makes things a little bit more unpredictable. Things hear you, and some things never hear you, so you can get caught off guard, which is it's just quite interesting. That can all be found in AI.fs. I use the original source as a heavy reference to this because I want it to be, reflective of how of the original game, and it was difficult to do through observation alone. So I dove into the source. So talk about this because I think this is really interesting. At the time, the game had to be downloaded over really small bandwidths. I think I had a 14.4 baud modem at the time. Which is, puny. Even my rural broadband has more. Or it was distributed on a floppy, so you had to squeeze things down. And I know it's still the case now. Obviously we've got graphics cards which support texture decompression and things. It's still a problem today, because things are much bigger. The asset files are double compressed. There's a typical sort of run length encoding system that is used. But then there's also a sort of a secondary compression, which is called Carmack compression, after John Carmack. It's his compression algorithm, and it allows for similar blocks of bytes to be replaced with pointers. I've never done LZW compression, but I think that's similar to LZW compression. It's his own format for doing it. So things are double compressed. And again, we just load up those raw bytes and we start decompressing those bytes using those two algorithms. And if you want to look at that code, it can be found in compression.fs. It's very simple, but it's a good example of the sort of code that you get into with this kind of stuff. Let's try and find the thing. If I can't find it, we'll move on. Assets. We'll just move on. I can't. Oh, there it is. Senior moment. Yeah, so there's a run length. Again, it's quite functional and it uses an unfold. Again, I try to keep this fairly functional, this code, which was quite interesting to twist these things into that shape. I didn't use original source code to figure this out, but I did find somebody who'd done this in JavaScript, I think. So I kind of looked at his JavaScript and based it off that and made a few tweaks. But they're the two compression algorithms, which are quite interesting to look at. Yeah, so that's pretty cool. Maps we talked about, just a reminder. I won't talk about them much now because we're running out of time. Graphics are in weird formats, and originally I was sort of decompressing some and others. I had issues decoding some of them, and so in the end, this was supposed to be a fun project. I didn't really feel like beating my head against a wall with weird formats forever. So I used a few tools to extract from them the audio, which are listed at the bottom. They're open source tools, mostly on GitHub. The text is stored in a way that was to facilitate quick rendering to the VGA mode that was used at the time, but it feels a bit strange to somebody in like 2023. And finally, the thing I wanted to get to before I finished was targeting the desktop. If I'd have set off with kind of targeting the desktop as a goal right at the start, I would have probably built some abstractions for that purpose, but I didn't do that. I just set off with JavaScript. So the abstractions that I used to make this cross-compile with a desktop are not particularly purposeful. We were basically, instead what I did was I looked at the JavaScript that was the code was specific to the JavaScript runtime, so data view, UInt32 array, and I basically wrote .NET versions of those back to us onto .NET structures, so that I could use the same code. I used image sharp to represent the textures and let me see and get the pixels. And again, I use the same approach. I render the output to a texture, and I use OpenGL to put that onto the display. So I do use OpenGL, but it's literally because I just needed some way of getting a graphic onto the screen performantly, to transfer it over performantly. That's mostly it. It's a bit of a hack because I didn't go about it in a purposeful way, but it does work. And in fact, if I desktop Wolfenstein run it, we should see there's Wolfenstein, the same code running in .NET. I don't know if you hear the sound, but it's just gone badly wrong. It's not. I've never had that happen before. Demo curse. Oh no. It crashed. I've never actually had that happen before. How embarrassing. Yeah, but it's the same code running in .NET. So I've lost a position in here as well now through that, getting me a bit confused. That's a whirlwind tour of it. If anybody's interested in it, I'm always happy to talk about it at more length and go through the code with people. You have to cover those concepts to even look at the code, really, have it make any kind of sense. So it's a bit of a whirlwind tour. They are some things I found useful on the screen here. Obviously, I've talked about many of them. And I guess that's it for me. I think I've hopefully ended on time. And I guess if there's any questions or comments, happy to answer them or try to answer them.
Great session, James. Absolutely great session. And great job also on the project. Now, one of the natural questions that you expect in this for some kind of this talk is how long did it take you? So I see in the GitHub repository 35 commits, 20,000 lines of code, something like that.
How long did it take me? I think it took. It was very part-time because my dog, who amazingly hasn't put in an appearance on this show because she normally does at the worst points, was a puppy. So I was doing it when she was asleep. I think it probably took me about 4 to 6 months, something like that. It wasn't a crazy long project. It was a while, but it wasn't like insane. It was doable, and I just broke it down to small chunks. And the bits I talked about here is literally how I chunked it down. So I could spend a weekend on it, around the dog being awake or asleep, and crack on with it. So it didn't take too long. The public commit originally wasn't a public repo, and there was another repo I was working on in private. It had some assets in it that were not from the shareware version, so I had to I just had to clean the repo down and republish it when I put it open source.
I was confused for a moment because otherwise it would have been in 14 days, something like that. So that's why we had to ask. Yeah.
No, it probably took me 14 days to work out those orientable sprites because that was a real head melter. Yeah.
Martin, next question. I think we have a couple.
I'm doing this thing
muted.
again where I'm on mute.
Yeah.
I think a related question there would be: would you do this thing again? Like if you could get a different title from the era where Wolfenstein 3D was released, would you do it again?
Definitely. So funnily enough, I've got a few things on the go. I'm doing an old BBC golf game called Hold Out, which is I'm doing in TypeScript and WebGL, which is kind of fun. And I'm writing. This got me kind of a bit inspired to start writing about game engine development for fun. So not writing Godot or Unity, hiss boo, flavor of the month for the last week or two, but not writing like a commercial game engine, but the concepts behind game engines are really fascinating. We're getting into all sorts of interesting space. So I've got a C# based game engine, a 2D game engine, which I've been writing, and I've been writing a book about how it works at the same time. And I started to sporadically publish some of that. The book's actually quite well written, and I've been kind of publishing bits of it, but I've not really got into a rhythm in terms of outputting it. So I'll definitely do it again, and I am doing it again. And there's a whole bunch of games I'd like to visit of different styles. I've got a real hankering to do Elite, If you remember Elite from the I've got a real hankering to do a .NET version of Elite. And
there was just a question about what's the next remake.
Yeah, I think it'll probably be Elite. Yeah.
Right now, the poll that we have going in the chat is it's going between Lemmings and Dune 2, it seems.
Oh, both were interesting. Yeah. Dune 2 was like another formative game that had me running around my house with excitement. And Lemmings was just everywhere, and I played it on so many machines. Writing an RTS is really interesting to me. It just interests me. I've done quite a lot with pathfinding and things, so some stuff I know. But yeah, I love that era of gaming, and it's really interesting to port them across to modern languages because they take you in some fascinating directions in terms of things you learn and have to think about, which you just wouldn't encounter in, a sort of in your day job unless you're working in, I guess, the games industry, which is not something I particularly plan on doing.
Will there also be multiplayer capability at some point? I mean, it's running in browser already.
So I was talking to a colleague I used to, an ex-colleague, somebody I used to work with about the game engine, and he was like, "Are you going to do a multiplayer? Are you going to do netcode?" I was like, "Oh my goodness, that's probably a book in and of itself, like multiplayer netcode." So maybe, but I'd like to finish the 2D game engine.
Sounds good. Sounds good.
Yeah, there's lots of things you could do. It's just interesting. It's whatever. I think it's wherever the curiosity takes me, I guess.
Did you have any experience prior to that, like from studies or anything, or was it really, like you said, the fascination and then getting into it?
It's just a fascination and getting into it, really. I sort of did maths to A level in the UK. I was always, I'm okay at maths. So I can generally figure stuff out. I'm better at maths than I'm at visualizations, which is why the orientable sprites eluded me for a while. The maths behind it was simple, but the visualizing it was difficult. I just it just interested me, and I just kind of learned what I needed. I guess I've probably got just enough mathematical grounding that I things like this are okay. But I'm not a mathematician for sure. But yeah, I just kind of got into it. I guess I wrote one of my first jobs was writing some graphics engines for training systems. But it's a long time ago. 96.
I would like to have one other question answered if possible. So Simeon, I hope the name is correct, asked for elements such as Raycasters. Are there NuGet packages for that? Do you know anything?
Not what I came across. I must say I wasn't looking for one, but there could be one. It would be pretty easy to take either the F# Raycaster or the C# Raycaster that I built and package them into NuGet, because the core of it is pretty abstract. They just need a set of textures and a map. You could easily repackage them into some kind of library. Maybe that'd be an interesting thing to do, because I don't think it'd be too difficult to sort of abstract into the NuGet Raycaster. Yeah, that might be fun.
I guess it's also hard to kind of standardize that for anyone to use it in various scenarios. And plus, where's
the fun? Yeah. I think the Raycaster itself would be okay, but you couldn't standardize the game. You could say, here's some game objects and bits and pieces, but yeah, it'd be interesting to see how much further you could go. But of course, Wolfenstein, the Wolfenstein engine was reused many times back in the early 90s by other games. So it's possible. Yeah, interesting.
It feels like I was at that very moment when a new engine was born. That's the vibe that I'm getting here.
Yeah, it was awesome. It was mind blowing.
Also, I'm very glad also to have seen Silk.net on your slides. We had a webinar with them some time ago. Awesome project as well. Also, I like
it's fantastic.
There.
It's amazing. Yeah, it's amazing. Yeah. Big shout out to that. It's amazing. I've used it a few times. It's amazing. Yeah.
Cool. All right, James. Thank you for your talk. This was great, I think, to open the conference with. There's going to be more talks as well. If you want to stick around, we have a quick raffle going with a question from your talk. So if the audience wants to win a .ultimate license, which is essentially all of the .NET tools from JetBrains, I have one question, and the first person to answer it will get the license. How do you avoid the fisheye effect when raycasting? Is that using the Euclidean distance or the perpendicular distance from the camera plane? And I promise not all questions are going to be so complex, but this one was fun.
Man, we need 10 minutes to actually write that answer.
Euclidean. I explained it right now.
All right, we have many answers. UVCW, we will be in touch. I see you in the chat. You're the first person. I will be in touch and arrange the license for you. With that, James, again, thank you for your talk.
James, I have one more. I have one more question. I see there have been a couple of answers, maybe unanswered. Maybe if you got the time, check the YouTube chat once more, and because I think people would be curious to know. Yeah, some questions have been left.
I'll take a quick look on YouTube.
All right,
I'll take a look on YouTube.
Then thanks.
Great. Thank you, guys.